The theory of perfect competition predicts that self-interested behavior by individuals, when combined with competition, can lead to an efficient allocation of resources. This prediction is only valid in markets for private goods. A private good has very special characteristics. It is excludable in the sense that its owner can completely and costlessly prevent other people from using it, and is completely subtractable in the sense that each unit of a private good consumed by one individual removes one unit from the consumption available to other individuals. Moreover, a pure private good generates neither beneficial nor detrimental externalities. Economic theory also predicts that some other markets will lead to inefficient, suboptimal outcomes. Some of these cases involve monopoly, externalities, and public goods. In this lecture, we investigate whether public goods markets really are inefficient. Pure public goods are the opposite of pure private goods. They are neither excludable nor subtractable. A good example is the access road to a cottage. Imagine a group of 4 cottages on a lake with no road access. Building a road to the cottages will raise their value, but the road is so expensive it is not worthwhile for any one cottage owner to build it. One of the cottagers suggests that everyone chip in $1,000 to build a road. These numbers illustrate the problem. Let's suppose that without the road, owner 1's cottage is worth $2,000. If some other owner contributes $1,000, only a very poor road can be built, and the value of the first owner's house goes up by $750 to $2,750. If 2 other owners contribute $1,000 each, for a total of $2,000, a better road can be built. The value of the first owner's house rises by an additional $750 to a total of $3,500. Similarly, if 3 other owners contribute a total of $3,000, the value of the first owner's house has risen to $4,250. Things are not so rosy, however, if the owner has to pay for the road himself. This column indicates that if the first owner contributes $1,000 when the other owners contribute nothing, his net wealth will be $1,750. $2,750 for the cottage with a $1,000 road, less the $1,000 spent on the road. This is $250 less than the case of a 0 contribution. Similarly, if the other owners contribute $2,000, owner 1's net wealth will be $3,250 if he contributes, while it will be $3,500 if he does not. Pretty clearly, the owner of the first cottage is better off not contributing to the road, no matter what the other owners do. This is called free riding, since the owner will benefit from whatever road is built without contributing towards it. Free riding is the owner's dominant strategy because it gives the highest payoff regardless of the other's choices. Economic theory predicts that individuals will adopt their dominant strategy, and hence that all owners will free ride. But if everyone free rides, the road will never get built, and all of the owners will be worse off than they might have been. This table shows that the net wealth of the 4 owners together is $8,000 if they all free ride, but $16,000 if they all contribute to the road. Thus, we have a conflict between the individually rational behavior of free riding and the collectively rational behavior of voluntarily contributing to the public good. This situation is often called a social dilemma. In a social dilemma, the group is best off if everyone cooperates. but each individual is better off not cooperating, assuming the other actions don't change. Social dilemmas have been studied by economists and many other social scientists. Many have asked whether people actually act as non-cooperatively as economic theory predicts. A group of economists and political scientists at the University of Arizona in Indiana have been studying social dilemmas for some time. Some of their experiments are very similar to the example of the cottage owners that we have just examined. In one experiment, groups of 10 subjects were given payoff tables like this one. Each individual was given 10 tokens which could be used to contribute to a public good. Any tokens not contributed to the public good were used to buy a private good. The payoff table shows how the net payoff to an individual depends on the subject's own contribution and the contributions of the others in the group. Notice how the structure of the table is similar to our example. If no one contributes to the public good, this subject's payoff is 10. If some other subject contributes 1 token to the public good, the first subject's payoff rises by 3/10 of a token. The experimenters call this the marginal per capita return, or MPCR for short. Because the marginal per capita return is positive, this subject's payoffs rise continuously as other subjects increase their contributions. It reaches 37 when all the other subjects contribute all their tokens and this subject contributes nothing. Notice also that this subject's payoff decreases as his contributions to the public good increase. This is because the marginal per capita return of 3/10 of a token is less than the value of the token. The subject actually loses 7/10 of a token for each token he or she contributes to the public good. No matter what contribution the others make, this subject is always better off contributing nothing. Once again, free riding is the dominant strategy. This table shows the payoffs for the group as a whole. The top left cell, containing 100, shows that the group is worse off when all subjects follow their dominant strategy of free riding. The bottom right cell, containing 300, shows that the group is better off when all subjects follow the cooperative strategy of contributing all their tokens to the public good. Once again, we have a social dilemma. Mark Isaac and James Walker, 2 members of the Arizona and Indiana group, conducted a number of sessions using this payoff structure. In each session, subjects were given 10 opportunities to decide on a contribution without communicating in any way with the others in their group. This figure shows some of their results. The line labeled 10L shows the average contribution per period calculated across many sessions and expressed as a percentage of the optimal contribution. The line shows that in the first period, subjects contributed about 47% of the optimal number of tokens. This behavior puzzles economists, since they would have predicted that no one would contribute anything. Of course, it is also disappointing behavior for those who believe cooperation is a good thing. The line shows that matters actually get worse the longer subjects participate in the experiment. By the 8th period, contributions have declined to about 20% of the optimal level, and in the last period, they declined even further, to about 10% of optimal. 2 conclusions can be drawn from this data. First, the theory of public goods is correct in predicting some market failure. Very clearly, average contributions never approach the socially optimal level. Nevertheless, economists seem to be too skeptical about human nature. Substantial contributions to the public good were made, even when the dominant strategy was to free ride. Isaac and Walker wondered how general their results were. they conducted some other sessions in which subjects were given payoff tables with a higher marginal per capita return of 3/4 of a token. Free riding was still a dominant strategy for all players, but the gain from free riding was reduced. This figure shows that on average, subjects in these sessions, identified by the line labeled 10H, contributed substantially higher fractions of the optimal number of tokens. Isaac and Walker also investigated whether smaller groups would be able to coordinate their actions better. Here there was something of a surprise. Line 4L shows that 4-person groups with low marginal per capita returns experienced a faster and more complete decay of contributions. But 4-person groups with high marginal per capita returns started off as cooperatively as the comparable 10-person groups and actually increased their contributions during the early periods before experiencing a gradual decline later in the sessions. We can summarize these results as follows. Laboratory experiments confirm that the provision of public goods will be characterized by market failure when communication is not permitted. Allocation is generally inefficient. The average level of contributions begins well above the dominant strategy of free riding, but these contributions decline over time. In many circumstances, however, they remain significantly above the free riding levels, while still well below optimal or efficient levels. You may wonder why I stress there was no communication in these experiments. The reason is simple. Just like the results of market experiments, the results of public goods experiments depend on the rules of the game. It turns out that rules governing communication are particularly important. Another experiment by Isaac and Walker shows dramatically the importance of communication. In this experiment, subjects were once again presented with payoff tables like those we've seen, and contributions to public goods were made for 10 periods. At the end of the first 10 periods, the experimenters announced that there was time for 10 more periods. Sometimes, however, the rules governing communication were changed for the second 10 periods. This figure shows what happens when no communication is allowed. Just as before, contributions start at about 50% of the optimal value and decline to close to 0 by the end of the first 10 periods. Note what happens for the second 10 periods, however. When the session is restarted, contributions rise to 40% of optimal. Subjects are trying to reestablish cooperation. Over time, however, contributions once again decay to close to 0. In other cases, Isaac and Walker changed the rules after the first 10 periods. In the sessions shown here, no communication was allowed for the first 10 periods. The results are just like the earlier ones. But in the second 10 periods, subjects were allowed to meet before each period. They were free to discuss the situation and agree on their contribution level. For a number of reasons, including the fact that there was no way to enforce an agreement, many economic theories predict that everyone will free ride. In fact, however, contributions started at about 60% of optimal levels and rose to close to 100% of optimal. Clearly, communication helps people solve social dilemmas, even when enforcement is not possible. The colored lines in this figure show the results of communication even more clearly. In these sessions, subjects were allowed to communicate for the first 10 periods, but not for the second 10. Contributions started high and did not decay. In fact, 100% of optimal contributions were made in the first, sixth, and last 4 periods. Even when communication was prevented in the last 10 periods, The effect of the previous communication lasted a long time. Contributions remained at almost 100% of optimal until the last 3 periods, when they decayed slightly. What have we learned from these experiments? First, we have shown that economic theories about market failure can be tested in the lab. Second, we have learned that economic theory is correct in predicting that markets for public goods will be less than perfectly efficient. But also we have learned that simple economic models don't always capture individual behavior. When communication is allowed, the voluntary provision of public goods is much higher. Thus, we have shown that in some cases, groups of individuals can make significant progress in solving social dilemmas related to public goods, even when no enforcement is possible. And finally, once again, institutions matter. These results have important implications for public policy. They indicate that it is not always necessary for governments to supply public goods. In some cases, local cooperation may be sufficient to achieve a close to optimal solution. We should pay particular attention, however, to the conditions under which an informal resolution of public goods dilemmas can be achieved.